Hello, it's Adrian with the automation group at Gerrie Electric. In this video, we're going to have a look at the adaptive control or adaptive tuning as part of the TotalForce technology, which is standard on all PowerFlex 755T drives. And we're going to have a look at the simulation where we're trying to reproduce some of the mechanical resonances that can be introduced in a real system and how this technology helps to eliminate those and have the system running as smooth as possible. Adaptive control, we are able to reduce the commissioning time and mechanical wear, and at the same time, we are improving the application performance. Looking at the two components of the adaptive control, the load observer will automatically compensate for any changes in mechanics and compliance. It's very useful for applications where inertia varies during the operation, and at the same time is going to reduce the need to make any manual adjustments. The other component, the tracking notch filter, will help to increase the application uptime by blocking any harmful resonance and vibration. It's going to automatically adapt to changing frequency over time, and it's going to be used as an indicator to proactively monitor the machine performance. We're going to spend the next couple minutes looking at a simulation that is going to show us how the resonance are looking into a system and how the PowerFlex 755T with the adaptive tuning is able to counteract all those and make the system run smoothly. On the screen now, on the left lower corner, we have a video of the actual physical stand as it is in our lab. The stand consists of an electrical motor. On the electrical motor on the left side, where you can see a gray piece of wire, there is an encoder. Very important to remember, the adaptive tuning, it's a closed loop control. So without the encoder, we're not going to be able to actually get the velocity feedback from the motor, and the process will not be able to be activated. The motor is attached to an axe, and the coupling that is used is very loose. That way, we're introducing some resonances in the system. And on the axe, you can see with some yellow markers on them, there are two flying wheels. Those two flying wheels, they're actually out of balance. And that way, we ensure that we're introducing some low frequency resonance in the system. The axe is installed on two bearings that are very loose as well. And the material that we used for the actual axe, for the rod, it's a flexible one rather than being a rigid one. And that way, we introduce even more vibration and resonance in the system. On the top left corner of the screen, we have a faceplate that is used to control the drive. We can start, we can stop the drive, we can see some of the parameters of the drive, and also we can enable and disable the two components of the adaptive tuning, the load observer and the tracking of the notch filter. On the right top corner of the screen, we have a trend that is going to help us to monitor different parameters from the system. And we're going to look in red, we're going to have the torque reference output. In green, we're going to have the velocity error. And in purple, we're going to look at the velocity feedback. Without having any of the adaptive tuning features enabled, let's start the drive and let's watch the trend and see exactly what's happening with our velocity, with our torque, and with the velocity error. Okay, so this doesn't look very good. As you can see, the velocity error, it's all over the place. The torque reference, it's trying to compensate, and again, it's going all over the place. And in purple, the velocity feedback has some variation. It's not looking very good. Let's try now and see if we're starting to enable the two components of the adaptive tuning, what's happening. So we're going to start by enabling the load observer, and we're going to start again the drive. It's not looking any better. By all means, it's looking a little bit
worse than it was before, and that's because the amplitude of the torque reference it's even higher than it was before. The reason of why this is happening is because with the load observer, we're actually eliminating any of the lower frequency resonances in the system, but we're not dealing with the higher ones. And that's what it's actually causing the change in the amplitude for the torque reference. So let's enable now the tracking notch filter and see if anything changes. Okay, so I think we all can agree that it is looking way, way better than what we've seen before. So even if we have lots of issues in the mechanical side of the process, the drive through the adaptive tuning is able to eliminate those and have the process running very smoothly. If you're looking at the beginning of the graph where the velocity feedback is ramping up, the purple line, there's still a lot of changes in the torque reference and in the velocity error. But once the drive is reaching the reference speed, it's starting to eliminate those. And we can see very fast the drive is able to actually smooth all the lines, including the velocity feedback, the velocity error, and the torque reference. So obviously, by using the tracking notch filter, we are able to eliminate all those higher frequency issues which are introduced by the loose coupling, by the fact that the axe is a flexible one instead of a rigid one, and we are also able to counteract any of the effects of the loose bearings that are holding the axe into the place. So using the adaptive tuning feature on the PowerFlex 755T, we are able to take a mechanical system which has all kind of issues and be able to run that very nice and smooth and be efficient. Now remember, any system that has those kind of issues, you still have to fix them. But that at least will give you the time to schedule the maintenance and maybe to obtain any of the parts that are necessary to be replaced in the system. Thank you for watching today, and please don't forget to visit our YouTube channel for more videos.